All right, guys, we are going to try something new and different today. We are going to do polar graphing. Polar graphing is useful for professions like air traffic controllers. So when we plot a point in the XY coordinate system, we just talk about going over and up. But air traffic controllers record the locations of airplanes using distances and angles like a polar coordinate system. They have to know, because two planes can be in the same distance away from the air traffic controller or the air tower, but if they're at different heights or different altitudes, they're not going to crash into each other. So they use a polar coordinate system. Okay. In a polar coordinate system, the origin is a fixed point called the pole. So the pole is the origin. The polar axis is an initial ray from the pole. It's usually the horizontal axis and directed to the right. That's what we're going to use. I'm not sure. In air traffic controlling, they may use north as the polar axis, but we're going to use the positive x-axis. All right, the location of a point in the polar coordinate system is identified by r and theta instead of x and y. R is a radius or distance out to the point, and theta is the amount of turn in the counterclockwise direction off that polar axis. Now, when r is called a directed distance, okay, from the pole, no, theta is the directed distance and a directed angle, and r is a directed distance. Anyway, positive values of theta go this way, negative go the other direction. Get a page down here. All right, so you are going to get graph paper kind of like this. This particular graph paper I'm showing you here has more marks than most. Most of the time you're just going to see the pi over 6, pi over 4, and pi over 3. Okay? So it's going to look more like, well, this one has the other ones. They're just not labeled. Okay? So usually they have all of them. They're just not necessarily all labeled. All right. One more time, when we're measuring in this system, the pole is the origin and the polar axis is the positive x-axis. And our xy ordered pairs are no longer x and y, they're r and theta. And the r is the radius. It tells us how far out to go. And theta is an angle that tells us how far around to rotate. Now, this graph paper has circles. See, this is a radius of 1, anywhere on that circle. This one out from here to here is a radius of 2. If we go out to this circle that looks a little darker to me, would be radius 1, 2, 3, 4, 5. So all the points on this circle have a radius of 5. That's how you're going to count r. All right. So to plot a point like 3 and pi over 4, you would rotate around to the pi over 4, which is actually halfway in between. Pi over 4 is like 45 degrees, so it's halfway between here and here. It's just not marked on this one. And then 3 means you're going to go out from the center a radius of 1, then 2, then 3. Right to there, 3 pi over 4. Okay? It's the third circle out. Sorry, wrong way. Now, it gets complicated quickly because you know you can do negative rotation. We understand that idea. You go a negative 120 degrees this way, and you wind up on this 240 line, okay? But a negative radius means that you go backwards 2.5. So you end up going 1, 2.5 back into this quadrant. Now, what that means is that there are multiple names for every point. So this particular point was on the 60-degree line, and it was 2.5 positive in that direction. and it's the same location as this. Okay, so points have multiple names. So we're going to practice real quick with some degrees. Most of the polar graphing we're going to do is in radians, but to start us out, we'll talk in degrees because we're more comfortable with degrees. 60 degrees of rotation and go out 3 circles would be R. 90 degrees in the negative direction would be this line down here at 270, and this one says go out 4. 1, 2, 3, 4. So that dot right there would be T. This is in radians, okay? It says go negative 4 pi over 3. Well, if you think about where that is, let me make this a little bit smaller so I can see it better in the recording window. Okay, so positive 4 pi over 3 is all the way past pi, 1, 2, 3, 4 marks. So if you're going to go negative 4 pi over 3, you're going to go past pi, 1, 2, 3, 4 marks, which is here, positive 2 pi over 3. You could add 2 pi to this, and you'd get positive 2 pi over 3. But that's where you're at. Now you went in a negative direction, but that's it. And then you're going forward out 4 circles. 1, 2, 3, 4. So Q is right there. You just rotated this way to get there. This one says rotate a positive pi over 6, so we're on this line, except we're not on that line. Supposed to extend it across the circle and go backwards 2. So 1, 2 would be here. All right. So again, we have degrees, a negative 150. Well, positive 150 is almost to 180. Negative 150 would be here on this line. And then, but we're not supposed to stay there. We're supposed to go backwards, which would match up with the 30 here if we did 180. And we're supposed to go backwards 2.5. 1, 2.5. So we're right here at A. Last one in degrees, 420. So this would go all the way around 360 and another 60. So it's going to land us here on this 60-degree line, but we're also supposed to back up, which would be the 240 line, 4. 1, 2, 3, 4. So B is clear over here. Now, we're going to practice finding more names for these. This one very obviously could have been 30 and 2.5. This one could have been positive 240 and 4. Okay, they're trickier in radians. So here it says we have the point 4, 135. So 135 is this line. We're going to go out 4. 1, 2, 3, 4, and put a point, T. Now we're going to name it with 3 more names for a total of 4. The first one was a positive, positive. We could have gone negative this way, so that would be 135 minus 360, which is what, 360 minus 135 is 225. So we could have said I'm going to go to that same spot, but I'm going to rotate a negative 225 and then out 4. So that's a positive negative. Now the other option is we could use a negative R value. If we went all the way across the circle over here, we'd be at the 315 line. So we could have rotated around to the 315 and then said, well, I want you to back up 4, so you're going to go negative 4. Or we could have rotated just this little negative 45 degrees here and then backed up 4. So we covered all the possibilities of positive, 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 negative, negative, positive, negative, negative. And they all landed us at the same spot. So we are to find 3 additional names for this spot. And the first one here is in degrees. So it says go around to 240 and out 5. 1, 2, 3, 4, 5. All right, so that, I don't know, it says 3A, I'll call it A, I guess. That's one way to get there. We could have also said I'm going to go negative 120, right? 360 minus 240 is negative 120, and out positive 5. There's a positive negative. We could have said the opposite of that is 60 over here if we subtract 180. We could have said I'm going to rotate positive 60 degrees, and then I'm going to back up 5. Or I'm going to rotate, let's see, to 60 would be negative 300 degrees. And then when I get over there to 60, I'm going to back up 5. All right, so we got 3 more names that fall between 360 and negative 360. Okay, and have a radius of 5. All right, now we got to do radians. Okay, here we go. Pi over 6 is this line right here, and we're going to go out 2. And I'm going to call this B because it's problem 3B. Okay. We could have gone, pi over 6 is the first one, so we could have said I'm going to go negative 11 pi over 6. That's all the way around but 1. And out 2. Or the line straight across from pi over 6 is 7 pi over 6. Okay. And we could have said I'm going to rotate 7 pi over 6. And then I'm going to back up 2. All right. Or what if we rotated a negative to here and then backed up 2? So we have a negative rotation and backed up 2. We just got to figure out what that negative rotation is. Well, it's 90 and 2 more marked ones. So if we were going this way, it would be 90 and 2 more marked ones. So it's negative 5 pi over 6. You could change it to degrees. You could look at your unit circle and see if it's a little bit clearer on there. You could say it's pi over, well, we're going, what are we doing going this way? Negative. How much negative is that? So you could do 2 pi or 7 pi over 6 minus 2 pi, which is 7 pi over 6 minus 12 pi over 6. And that would give you the negative 5 pi over 6. Okay? Whatever works, but because we backed up, remember, those are all names over here for B. All right, so this is just practice. I kind of feel like I should skip this. Maybe I'll do, I don't know, just a couple quick questions. They are all in radians. Like C here is negative pi over 3. Well, pi over 3 is 1, 2, 3, 4 lines this way. But I'm supposed to go negative 1, 2, 3, 4 lines this way. So this would be negative pi over 3. And then I'm supposed to go out 3. So 1, 2, 3. And that's C. Maybe this last one? I don't know. Negative pi over 6 would be 2 lines but go in the negative direction. And then we're supposed to back up 3, which is going to be this 5 pi over 6 line over here. 1, 2, 3. So that's F. All right. I did F and I did C because you were rotating in the negative direction. If I did E here, you'd go to 4 pi over 3, which is this one, but then you're supposed to back up. Straight across is pi over 3. Back up 1, 2, 1, 2 and a half would be here. All right, so you guys can finish those and check them on my work. This is giving different names again. I should let you do this one on your own, probably. So you go 5 pi over 3, which is all the way over to here, and out 2. 1, 2. Now, that leaves you 4 lines this way, and 4 lines is a pi over 3. So we could have called this a negative pi over 3 and a 2. Or we could have said that we were going to go to this guy over here, which is a 2 pi over 3, and then back up 2. Or if you were going to go this way, you'd go all the way past here to 2 pi over 3, which is actually the same distance as 4 pi over 3, so a negative 4 pi over 3, or take 2 pi over 3 minus 2 pi is 6 pi over 3, gives you a negative 4 pi over 3, okay? And then if we get to this negative 4 pi over 3, which is really positive 2 pi over 3, you would have to back up 2. I am not on the right spot, am I? This is 3, not 2. I do that all the time. So it should have been here that whole time. Sorry, guys. All right. I'm just, anyway, okay. Then the last thing I'm going to show you today is the fun part. We're going to do graphing on the calculator. So you're going to take your calculator and you're going to go to mode and you're going to go to radians. But then you're going to go down below to function and over to the right to polar. So we are at radians, and instead of function, we're going to hit enter when we're on polar. So it should now say at the top, when we hit clear, okay, it says radians. I don't know if this MP is mode polar, maybe. Okay. But the question we have, look what happens when we go to y equals now. It's no longer a y equals, it's r equals. If we were to put r equals 2, it would just draw a circle of radius 2. But before we do that, I would like you to do what it says here. It says go to the window and change theta from 0 to 2 pi. So type 0, enter, and then go down and type 2 pi, enter, and it's going to put a decimal in there, and make the step 0.1. It doesn't really matter if you leave it 0.13, but you don't want to leave it 1 or 2 because it will only it'll only connect every 1 or 2 points instead of every 1/10. We want it to find a lot of points so it does a smooth curve, and I can show you what happens if you don't in a second. The x is supposed to be negative 4 to 4, and I'm going to go ahead and put a scale of 1, and the y I'm going to do negative 4 to 4 with a scale of 1. But then it says, then do a zoom square. If you do zoom square, after you've set that window up, what do I have wrong? I don't have a negative 4 here on my min. Oops, well, I still don't. If I do go to, it should show me exactly where the problem is. There we go, negative 4 to 4. Now, if you do a zoom square, it actually will change your window a little bit. It'll change the x's, but that's okay. It's just making the scale the same going across as it is up and down, because you want this to look like a circle. If you didn't do the zoom square, it would be oval shape. That was when we just put a r equals 2. But we're going to show you what fun happens when you put trig things in. We're going to do 2 cosine 2 theta. 2 cosine 2. And look what happens when you hit this X button. You actually get a theta now. So when you hit graph, it draws this adorable little flower with 4 leaves. called a 4-petaled rose. Okay. Now I want to show you a couple things. If you go to window and you were to change this step to like 1, it only measures every 1 and then it connects them in a straight line. Isn't that crazy? So instead of putting in 1/10, 2/10, 3/10, 4/10 and calculating them out, it's only calculating every 1. So you don't want to leave the step. You got to make the step small, but not too small or it'll take forever to calculate. All right. So that's a nice smooth 4-petaled rose. Now what you should notice is that these go out 2. That's actually the number in front is stretching the petals up to 2. And the second thing you should notice, the 2 actually tells you there's going to be 4 petals, and that's on your sheet. You don't have to memorize that. I don't even have it memorized. But eventually we will talk about symmetry. This one happens to be symmetric with both the X and the Y. Generally, anything with a cosine is going to have X-axis symmetry. That should sound familiar. Cosine goes with X. Okay. The next one we're going to do for fun, and then I'm going to let you do the rest for homework, is 1 + 2 sine theta. So I'm going to go here and type 1 plus, y equals 1 + 2 sine theta. Now, this time I'm doing sine, so this is going to have y-axis symmetry. And the 1 plus actually does something completely different. It's not a rose, okay? It is called a limicon, and it has y-axis symmetry here. There is a pronunciation somewhere, maybe on one of the notes. I don't know. But it's French, and I'm probably saying it wrong, but I see it limicon. I think that's how you say it, limicon. And I think of it like the inside of a lima bean. Lima bean to me. That's what that looks like. So anyway, that's just my little hint. And what it did again, this was only 1 unit tall. And then as it came back around, it was through 1. And then it went up to 1, 2, 3. Here. Whoa, mine is horribly not round. Okay. You don't have to graph these. You just have to do some matching problems. They're kind of fun. All right. So all of this stuff is made from polar graphs. And I think this is the end of the first part of the video. Oh, no, a little bit more here. These are the polar graphing problems, the special ones, okay? It says anything with cosine will have x-axis symmetry, and anything with sine will have y-axis symmetry. And these are the formulas right here that give you circles. You don't have to know this. It's just a reference sheet. Anytime you put 1 plus or minus sine or cosine, you get some kind of limicon. Some of them are called cardioids because they look more like a heart. They don't have the dimple inside or the inner loop. Roses, if you do cosine, you get ones that have x-axis symmetry. If you, like these, see how this one has an odd number of petals, but it's symmetric with the x. When you do sine, it's an even number, the y-axis is symmetric. If you put in, it says here, if n is an odd number, you will get n petals. If you put 2 times n in, you'll get you get twice that many petals if n is even. All right, I didn't explain that right. So if you wanted a 3-petaled rose, you would say sine of 3. If you wanted them to be 5 units long, you would put a 5 out front. If you wanted 8 petals, you would put a 4 because anytime you put an even number in, you get twice as many petals. So by putting a 4 in here, you get 8 petals. And if you wanted them to be, say, 2 units long, you would do that. I only tell you this because it's fun to graph these. You can also graph what looks like an infinity or a spiral. The spiral is really hard to set the window up for. I can do it in a meet sometime if anybody reminds me. All right, that's part 1.